Hello everyone, welcome to today's presentation. I'm excited to share insights on power calculation in high voltage systems. The title of our talk is Power Calculation and System Components. We'll explore how power is determined using the formula involving voltage, current, and power factor, and we'll look at key infrastructure elements like HV lines, civil bases, GIS halls, transformers, and monitoring systems. Over the next few slides, I'll guide you through the concepts, examples, and the practical aspects of managing high-voltage power systems. Let's get started. Let's take a closer look at the isometric power flow. Here, we see the step-down ratio, which is a key concept in understanding how voltage is transformed in power systems. The ratio is calculated as V1 divided by V2, which in this case is 380 volts over 132 volts, giving us approximately 2.88 to 1. This means that the voltage is reduced by nearly 3 times as it passes through the transformer. This step-down process is essential because we generate high voltages for efficient transmission, but we need lower voltages for safe and practical distribution to consumers. The diagram highlights the flow from the transmission line, through the transformer, and then to the bus bar, which acts as a central point connecting various components. From there, power flows through feeders to reach the loads. Understanding this flow helps us see how the different parts of the system are interconnected, ensuring power is transmitted efficiently and safely from generation sources to end users. It's a fundamental aspect of power system operation, tying together the transmission, transformation, and distribution stages seamlessly. Let's take a closer look at civil and electrical integration in our project. Here, the focus is on ground resistance, which is crucial for safety and system performance. The formula R equals ρ divided by 2 pi L times the natural logarithm of 4L over D helps us understand how ground resistance depends on soil resistivity, the length of the grounding conductor, and its diameter. This means that by optimizing these factors, we can reduce resistance and improve grounding effectiveness. Now, in terms of physical infrastructure, we have the control building, roads, earthing systems, access routes, and lighting, all of which are interconnected components of the overall civil and electrical setup. The control building houses the critical systems, while roads facilitate access for maintenance and operations. Earthing ensures safety by providing a low-resistance path to ground, and proper lighting keeps the site safe and operational during low light conditions. All these elements work together to ensure that our electrical systems are safely integrated with civil infrastructure, supporting both safety and operational efficiency throughout the project. Now, let's take a closer look at the 2D layout drawing. Here, you'll notice the key concept of clearance, which is calculated using the formula clearance equals K times the square root of V. This is crucial for ensuring safe and functional spacing in our design. For example, if we plug in a volume of 380, the clearance would be approximately 0.9 times the square root of 380, which comes out to about 17.5 meters. When reviewing the drawing, pay attention to the dimensions provided, as they define the size and scale of the layout. The north arrow helps us orient the plan correctly in relation to the actual site. Labels are used throughout to identify different sections and important features. Safety zones are marked clearly to indicate areas that require special attention or restricted access. And speaking of access, the drawing also highlights the designated doors or entry points, ensuring smooth movement within the space. All these elements work together to give us a comprehensive understanding of the layout, emphasizing safety, functionality, and proper planning within the overall project. Now, let's take a closer look at the exploded axonometric view. This type of diagram helps us visualize the different components of our electrical infrastructure in a clear and detailed way. One key point here is the elevation difference, denoted as delta, which we calculate using the formula L times the tangent of theta. This helps us understand how components are vertically spaced. You'll notice the various symbols, like the earthing grid, trench, GIS module, building, and layer labels, all of which are essential elements in our design. The earthing grid, for example, is crucial for safety, ensuring proper grounding. The trench represents the physical pathway for cables, and the GIS module is where all the management and control happen. Connecting these pieces visually through the exploded view allows us to see how everything fits together spatially, which is vital for planning and maintenance. This overall approach helps us ensure that our electrical system is not only effective, but also safe and easy to manage. So, keep in mind how these components interact and the importance of proper elevation and layout in the overall design. Let's take a closer look at the concept of the digital twin and the smart grid. Here, we see how the power loss, represented by P loss, is proportional to the square of the current I squared times the resistance R. By applying AI optimization, we can reduce this power loss by approximately 8%, which is quite significant for improving efficiency. This is where technologies like SCADA, or supervisory control and data acquisition, come into play, providing real-time monitoring and control. Coupled with IoT devices, we can gather extensive data across the grid. Automation then ensures that operations run smoothly and efficiently without constant human intervention. All of this feeds into the AI model, which analyzes data, predicts issues, and optimizes performance. The ultimate goal here is to enhance overall efficiency, especially with battery storage and energy management. So in essence, these interconnected technologies, SCADA, IoT, automation, and AI, form the backbone of a smarter, more resilient, and more efficient energy grid. They allow us to actively manage and optimize power flow, reducing losses and improving reliability across the system. Let's take a closer look at the sectional cut of the underground earthing system. Here, the key point is the voltage drop across the earthing grid, which is calculated as the current times the resistance of the grid, or I times RG. We need to ensure this voltage drop stays below 65 volts to maintain safety and system effectiveness. On this diagram, you can see different components involved. The earth rod, which is a crucial part of the grounding system, the trench where the cable is laid, and the soil layer that surrounds everything. These elements all work together to ensure a reliable connection to ground. It's important to understand how these parts interact because they influence the overall resistance and, consequently, the voltage drop. Properly designing and maintaining these components helps prevent dangerous voltages and ensures the safety of the entire electrical system. Remember, the main goal here is to keep the voltage drop within safe limits, and that involves careful consideration of each element in the underground earthing network. Let's wrap up with a quick safety check. The key metric here is the safety clearance factor, which is the ratio of the actual to the required clearance. For safety, this value should always be greater than or equal to 1, meaning we're meeting or exceeding the required safety margins. Now on this slide, you'll see icons representing critical safety features and personnel: the fire wall, the arc zone, the fence, relevant documentation, and the operator. Each of these plays a vital role in ensuring a safe operational environment. The fire wall acts as a barrier to prevent the spread of fire, protecting both personnel and equipment. The arc zone is the area where electrical arcs can occur, so maintaining proper clearances here is crucial. The fence helps control access, reducing risk of unauthorized entry. The documentation provides the necessary guidelines and safety procedures, and the operator is the person responsible for maintaining all these safety measures. Connecting this to our overall theme, consistently monitoring these factors and ensuring the safety clearance factor stays at or above 1 is essential for a safe and compliant operation. Always remember, safety isn't just a checklist, it's a continuous commitment.